We're having a look at Newton's laws, and before we do that, we need to quickly look at the forces involved in this chapter. We're going to look at them in detail when we look at Newton 3 again, but just for now, you need to know that the gravitational force is the force of the Earth on an object. Remember, for a force, it's important that you name both objects involved. The weight is then that same gravitational force of the Earth on an object. The normal force is the surface on that object, and friction is also the surface on that object, but the normal force is perpendicular. So the surface acting perpendicular on an object, and this is the parallel force of the surface acting on an object. Always against motion. Please remember that for this one. So we'll get back to those. But then you also need to be able to calculate the frictional force. Now we say maximum static friction or maximum kinetic friction, or not really maximum for kinetic, but for static, they say maximum static force because that's the force just before the object starts to move. So please be careful. If an object is sitting here on a surface, you did in chapter 1 that it will not slide if the downward force and the upward force are equal. So when this object is in equilibrium, this force up the slope must be equal to this force down the slope. And at the point just before it moves, that will give us the maximum static friction. So you will have to look out for those words in the question just before it moves or as it starts to move. Then you know that the downward force and the upward force are equal. Okay, but now more importantly for this chapter is that you have to work out the frictional force, and you have the equation on your information sheet is mu times by the normal force. Now the normal force is where I saw that some of you got confused. You can't just always say that the normal force is equal to the weight because it's not true. Only case where it is true is if you have an object on a flat surface, horizontal surface, and there is nothing else acting on that object. So if you have an object here, you have a force acting down, which is the weight. You have a force acting up, which is the F normal, which is the surface on this object. And because this object is in equilibrium, like we learned in chapter 1, the upward force and the downward force must be equal to each other, and therefore it will be easy to work out the frictional force because it will just be mu times by F normal, which then is the weight. Okay, so you can replace the F normal with W or Fg, it really doesn't matter what you use. Now the next scenario is if that box is still on that flat surface, but now it has extra forces acting in on it. So it has, for instance, a force pulling it upwards like that. So if we have a force that someone applies here, so we use Julian in the ASP, so let's just use him again. So the force applied by Julian in that direction, and that force is 20 newtons. Now you need to realize that that force, the normal force, is the force acting upwards on this object. But there's also a downward force here. So now if you think about it, is the surface still experiencing the same force, or is the box still experiencing the same force here? So now if you look at this, and that is why vectors was your very first chapter that you did, because now if you take that force, you can split it up into a horizontal component, so Fj horizontal, and you can split it up into a vertical component, so Fj vertical. You will see in the Siyavula exercises, they call it Fx and Fy. You're welcome to use that as well. It doesn't matter. So if that was a 10-degree angle, now you need to think, if this object is in equilibrium, F up and F down must still be equal. So now if you look at that, you've got F normal that is acting up, and you've got F Julian vertical that's acting up. So there's two up forces. We're still using the same F up equals F down that we used in chapter 1. So please don't think it's something new. So two forces acting up, and that must now be equal to your weight. But now we only want the normal force. So F normal is then going to be the weight minus Fj vertical. So only that vertical component. So it's going to be the weight minus 20. And if you look at it, I'm not going to explain the maths to you. It's the opposite. So it's 20 sine of 10 degrees. And that is then what gives you the normal force. You can think of it. The box is not pushing onto the floor that much anymore because Julian's lifting it up a little bit. So you have to minus that upward force. If you think about it logically, it also works out. You could also have exactly the opposite, where that 20 Newton force is pushing down on the block. So again, if that's my 10 degree angle, now it would mean that I've got two downward forces. So I'm just going to do the green bit over here. So now what is F up? So you then have F normal going up, but now you've got two, oops, not a plus, you've got two forces going down. So that's my upward force. And then you've got two forces going down. You've got weight plus F Julian vertical. So this force, the 20 newtons here, would again have a horizontal component and a vertical component. But this time it's pushing harder on the floor. So if you think about it logically again, we're going to add it to the weight. So that will then be W plus 20 sine 10 degrees. Okay, two ways of getting the normal force if there's extra forces acting on this object. And then the last one is if you have an object on an inclined plane. Now, I don't really want to talk too much about that because we spent too much time on that in chapter 1. But if you have an inclined plane and you have an object on an inclined plane, please remember, if this object is in equilibrium, which means it just stands still there is the weight that we can't escape from. It's the weight pushing down on the object or pulling down on the object to the center of the earth down is what I mean. Then we still have the normal force. Remember, the normal force needs to form a 90-degree angle with my surface. We call the normal force F normal or normal force, but not just normal. Please remember that. And then we have a force that stops this object from sliding down the surface, which is then the frictional force. So if we ask you for a free body diagram, all you're going to draw is a little dot with your frictional force, your weight, and your normal force. And I've said this so many times, leave it clean. Do not go and put components in there because that's what you get your 3 marks for, with labels, obviously. Now, if they ask you for the frictional force now, the maximum frictional force, if this object is in equilibrium, it should be equal to the force going down here, but you don't always know that. So they're not going to tell you. They're going to say calculate the frictional force and then determine if this object is actually standing still or not. So then you need to think for yourself, if there's a downward force here that's bigger, if this downward force, which is my weight parallel, is bigger than the frictional force, then this book will slide down. It was a book in your test. The object will slide down. But if it's not, then it will just stay there. So now what we need to do is work out the frictional force again. But remember, we have our equation. F friction is equal to mu times F normal. Now if we look at F normal, in this direction, there is no motion. So the normal force is going to be equal to the component of your weight that pushes this object down onto the surface. And this component here is always going to be weight perpendicular because it's perpendicular to the surface, the perpendicular component of your weight. And this will be the parallel component of your weight. But for the normal force, we're only interested in the perpendicular one. So if you look at and this we also did a lot of in chapter 1, if that's my theta there, this angle here will be theta. So it's going to be adjacent always. So weight perpendicular is going to be equal to weight times by adjacent, so it's cos of theta. So now here it's just going to be mu times by W cos theta. And that's always the case. So you don't have to really stress too much about it. I don't like rote learning, but this one could never be anything different. So those are your different normal forces that you could get. There was a question like this in your test, so just make sure that you can do it. That was the different normal forces. Make sure that you can work them out. Now for the free body diagram, as I already said, please now for the Newton section, make sure ask yourself, is this object moving or not? So the different scenarios, if the object is stationary and it's in equilibrium, so it's just not moving, then you have, if it was a free body diagram, remember it will just be a dot. You'll have your weight. Anything extra you can put in as dotted lines, but don't put it in as straight as solid lines, because then for every extra force you'll lose a mark. So that will be my weight, as I said earlier. That will be your normal force, and that will be your force of friction. So those will be the forces. Now, if in equilibrium, this frictional force will be equal to your weight perpendicular or your weight parallel, only if it's just not sliding. Otherwise, you need to calculate. And the same with the normal force. So please remember, now they're going to ask you about moving objects. Now, if this object is not just sitting still, you must remember that if the object is accelerating downwards, and this is what brings us to Newton's second law, and I'll talk about that again. So if it's moving downwards, yes, then friction will still be upwards. But please remember that if the object is moving upwards or accelerating upwards, then friction is not going to be upwards anymore. Then the friction is going to be downwards. So please read your question nicely and decide whether it is a stationary object or not a stationary object. Free body diagrams is super important in your whole paper. You will always get a free body diagram, and it helps you to solve Newton 2 problems, because if you have all the forces in a free body diagram, you can apply Newton's second law very easily. Moving on. Now we have the 3 laws. The first law says an object will continue in a straight line. So that means state of rest or uniform motion. It's always in a straight line. We don't look at curved motion. In its state of rest or uniform motion, please remember that is just saying that it's a constant velocity unless there is a resultant force. So now what does that actually say? So if there's no resultant force, they say unless acted on by a net force. So if F net is equal to 0. This law tells us that the acceleration will be 0 because the velocity is constant. Please, those 3 things always go together. If you see constant velocity, immediately think for yourself, there's no acceleration, no net force. And if you say no acceleration, velocity must be constant, no net force. The three facts must lead you to each other always. But how do they ask Newton's first law? It's normally an explanation question. And in that explanation question, they're going to have some scenario. So the typical question is you have something moving along in a car, on the back of a truck, anything. And it's loose. It can move. It doesn't have a safety belt on. So it's free to move if it could. Now they're traveling at 60 miles per hour. It's obviously an American example, but they're traveling. So that means the car, as well as the dummy, is moving at 60 meters per second or miles per hour. I'm just going to say meters per second in a forward direction. Now, remember what Newton's first law says. It will continue in its state of motion unless acted on by a net force. Now, if you look at what happens, the car hits the curb. So the car hits the curb. So the net force is acting on the car, not on the dummy. So this is the important part. They're going to ask you to explain the movement of the dummy using Newton's first law. So if you do that, you have to say that the dummy will continue, you can see it there in the law, continue at a velocity of 60 miles per hour, because that's what it was doing, unless it's acted on a net force, because the net force is acting on the car and not on the dummy. The dummy will only change this state of motion if it hits the windscreen like it does there, or it hits the floor over here. So the first net force acted on the car and not on the dummy, and therefore the dummy will continue at its constant velocity of 60 miles per hour in a forward direction. So if you say that the dummy starts to move, that's very wrong, because it was moving already. It wasn't in a state of rest. It was in a state of motion. And also be careful, if the question says use Newton's first law, it's a first law of motion. You need to talk about the velocity, not about the inertia, because inertia is now a property of that dummy. So if you look at the second definition there, inertia is a property of an object. So if you had to explain this using inertia, you will say the inertia of the dummy, property of the dummy, will cause it to resist a change in motion. So when the car changes its motion, the dummy will not change its motion and continue forward at a velocity of 60 miles per hour. Please, you need to use the correct wording for Newton's first law. Newton's second law. This is what half the chapter is about, and you'll see this pops up in all the other sections. Now, this is basically the equation that you get on your information sheet. So you can think about this logically, and we spoke about this, that as the force increases, if the mass stays the same, the acceleration is the same. So the force is directly proportional to the acceleration. And the mass is inversely proportional to the acceleration. Now, when you state this law, you can use this equation. Remember, your information sheet is important as a crib note because you get that equation. But please remember that Newton's laws are about the motion. It's Newton's second law of motion. So the law does say F net is equal to ma, or doesn't say, the law doesn't say that. The equation, we derive this equation from it. But remember, now in Newton's first law, there was no net force, so no acceleration. Now there is a net force, so there will be an acceleration. That's your first mark. If there is a net force acting on an object, there will be an acceleration. But now we need to talk about the motion. So we need to talk about the acceleration. So we have to say that the acceleration is directly proportional to the net force. You can see that. But the acceleration is inversely proportional to the mass. So these are the two facts that leads us to the equation. Now you will see that all the problems, now there's different types of scenarios. It's objects moving horizontally, vertically, rockets, scales. All of those questions is just an application of Newton's second law. And I'm going to record a separate video just to go through all the applications of Newton's second law. But what you need to remember is that it says F net equals ma. And for these questions, if you decided that this car is accelerating to the right, and most of the time the question will tell you that, that means that the forces to the right are going to be bigger than the forces to the left. So that means all the forces to the right must be bigger than all the forces to the left. And if you really simplify this, you can say that the forces to the right are winning forces and the forces to the left are losing forces. So when you think, what is F net? And that's your biggest job, you'll see when you look at the application questions. The If you want to look what F net is, you could always ask yourself which forces are winning, so it's the winning forces, minus which forces are losing, so the losing forces, is going to be, give me F net, which is going to be equal to the mass times by the acceleration. And if you think about that, it always becomes easy. So if I had a force engine, the force of the engine pushing forward here, remember, we want to know what is applying the force. So force engine is 2000 newtons, and we've got a frictional force going this way, which is 20 newtons. I like twos today. Then I know that the winning force is going to be 2000 newtons minus 20 equals ma. And you must always just think which direction is my acceleration, because that is going to be the direction that I make my forces all positive, and then I'm going to make all the forces in the opposite direction negative to get the acceleration in that specific direction. And I'll do all the different examples of lifts and scales and all those things with you in the next video. Last law. Newton's third law confuses half of you. You need to please get it out of your mind. And I say this with love to my friend Google. But please, you will get no marks if you say it's an action-reaction force, or for every action there is a reaction. Please, it is not wrong in theory, but it doesn't explain what Newton's third law actually says. You can look on FET, there are nice animations, and Khan Academy if you really want to go look online. But your books describes this very nicely. Newton's third law says, if object A exerts a force on object B, then object B exerts a force on object A with the same size but in opposite directions. And that is what is important. The forces have the same size, but they're just acting in opposite directions. So if I am, so now let's look at this scenario, because this is where the forces are going to become now very important. I'm just going to throw these things away because we don't need it now. And I am sitting there on the chair, knitting a scarf for my friend. Now, there are all kinds of forces acting here. I'm in equilibrium, so yes, the upward forces are equal to the downward forces, and the forces to the left are equal to the forces to the right, because I am in equilibrium. But these forces are forces acting on me only. So they are forces acting on one object. That means they cannot be Newton's third law pairs, because they are acting on the same object. Newton's third law says if object A exerts a force on object B, then object B exerts a force of the same size simultaneously. It must happen at the same time and at the same point. Object B exerts the same force on object A, but they are just in opposite directions. Now let's look at this scenario of me sitting in the chair in a little bit more detail, and look at the definitions. I put the definitions here for a reason again. If I ask you for the Newton third pair of Fg or W, so I say, what is the Newton 3 reaction force of the weight of the object? Now I'm testing that you know what the weight is, as well as that you know what Newton's third law is. Because the weight, you need to think, what is that force again? And remember, a force, you cannot mention a force if you don't have two objects involved. So the weight, if you look at the definition here, and I think I need to make it bigger because this was a problem. If you look at the weight definition again there, the weight is the gravitational force that the Earth exerts on an object. So if we look at the weight in my scenario here, it means the weight is the Earth on me. So this is the actual force. It's the force of the Earth on me. Now, if I need to know what the Newton 3 pair is, because the question says, what is the Newton 3 pair of the weight? Now, to get the Newton 3 pair, remember this was object A, Earth on me. So the Newton 3 reaction pair would be B on A. So it's the force of, please remember it's still a force, of kVs on the Earth. Please do not throw in a third object. There are only two objects involved here. The chair has got nothing to do with the fact that that I have a weight. If I move off the chair, I still have a weight. If I move anywhere in Joburg, I still have a weight. It's got nothing to do with the chair. So many of you want to put the chair in this scenario. It's not, we don't want a third object involved here. So that's the first one that they always ask. Then the next one, again, they're not going to say, what's the force of kVs on the chair? Because that would be too easy. If I say, what's the Newton's 3 reaction force of the force of kVs on the chair? That's way too simple, because all you're going to say, this is object A, this is object B, and you're going to say the Newton 3 pair is going to be the force of the chair on kVs. So, yeah, as you can see, I'm not going to ask you that. I don't think anyone will. That is why we use this as a chance to check your definition. So now if you look here, define normal force as the perpendicular force exerted by the surface on the object. So the question would rather say, what is the Newton 3 pair of the normal force? So before you can answer that, you need to know what the normal force is. So you have to say the normal force is the force of, as per the definition on the side, the force of the surface on the object. And it would be nice if you say the perpendicular force of the surface on the object, because the friction would be the parallel force of the surface on the object. So you can add that. So it's the force of the surface on the object. Now let's see. Remember, you need to decide what is A and B. It's the force of the surface on the object. No third thing must be involved here. So for my Newton 3 reaction force, it's going to be the force of the object, which is me. So kVs on the surface. So if we apply that to this question here, let's just use a more real type of example, because it's a bit wishy-washy if we do that. So if we say the normal force acting on me, okay, so what's the Newton 3 pair of the normal force acting on me? Again, what is the normal force on me if you forget about my feet? But here it will be the chair on kVs. That would be the normal force because it's the surface that I'm sitting on. So it's the chair perpendicular here on me. So that is the normal force, not the reaction yet. That's just the force given. So the Newton 3 pair would be kVs on the chair. Again, only two objects involved. A and B, B and A.